Hello, this is Dr. Kevin Garrison with a third video in a series of lectures on user-centered technology in education. Let's recap. 2 weeks ago we did this. We defined user-centeredness. We did so in the following way. We took James Kenevy's rhetorical triangle, which has the 3 R's, the reader, reality, and the writer, and we conceptualized the rhetorical triangle for a technological system. We used Robert Johnson's 1998 text, User-Centered Technology, to do so, and mainly what we changed in terms of the shift was we put the reader at the center of the equation, since the reader ultimately decides what happens to a text, and we applied that to a technological system, and made the user the center, quite literally, of the technological system. Why did we do this? Why did this matter? Well, last week we argued that it circumvents or counters technological determinism. Too often we center our questions about technology in one of 3 places. We put it in the artifact itself and the affordances that the artifact has, we put it in the system, or we give it in the hands of the designers or the so-called technocratic elite. We can counter technological determinism, in other words, take power back as a user and have freedom by simply shifting everything and putting users at the center of the technological world as opposed to the technology. In other words, if you use the physics metaphor, the sun is the center of the solar system, everything else revolves around it. It has the most power, gravitational pull. In 2017, technology is the sun. It has the strongest gravitational pull, and everything else is centered around that. Now, if we put the user at the center, then something remarkable happens, which is that we no longer have centralized control, but we have decentralized control. The way the decentralization works is that everybody has their own lived world experiences, their own way of thinking, their own ways of living, their own cultures, etc. And so when we listen to them, they are the ones that are put in charge of designing the next iteration of technological advance, rather than letting the technocrat do it, the artifact do it, or the system do it. So that's great. So we've defined user-centeredness, we've theorized about it, why is it necessary. This week we're going to do the following. We're going to apply it, the question of application. To do so, we're going to use Donald Norman's The Design of Everyday Things text. This is why we're going to focus on application this week. The students in the class are focusing this week on an artifact analysis, one of 3 that you'll be writing. The first one is asking you to take a space at your office or your place of work and analyze that space and analyze the artifacts within that space using the principles, the guidelines, and the heuristics that are found within this book. So what I'm going to do today is I'm going to demonstrate for you how that works so that you can take it from this abstract realm of theory and put it into a very concrete thing rooted in practice. The way that I'm going to do so is giving you a very detailed example of one that happened to me a few months ago when I was installing a basketball goal, and we'll break down this question of what went wrong and why. So here's my example. December 2016, I bought a basketball goal, a silverback basketball goal. It's an expensive top-of-the-line basketball goal. Got rooted in concrete, nice long tall post, 4 inches square, glass backboard, breakaway rim. This thing was top-of-the-line quality. I was excited by it. I wanted to have a basketball goal so that I could teach my daughter Kendall how to quite literally shoot for something. She's a little bit too young at 17 months to use it now, but I like to play basketball with my friends, so she gets the exposure of shooting the basketball, even though she's too young to actually do so. And it's the added bonus if I get to play with it. Now let me tell you what went wrong, and then we'll analyze why. Here's what happened. I got a pickup truck so that we can mount the basketball backboard and the rim to the post and the arms. Put that truck right here. The bed was right underneath these arms right here. I had a couple of friends stop by. These friends were young and strong, a 21-year-old and a 25-year-old. This basketball backboard weighs about 100 pounds. So each person was on either side lifting it up. 50 pounds per person doesn't seem like much, but you're lifting it over your head, and it's extremely awkward in terms of trying to keep it stable. So they had this thing up in the air. We're all three standing in the bed of a truck, and I had the hardware, and I had the nuts and the bolts, and I had the ratchet sets and everything. I was ready to go. They held it up in the air. I quickly pushed these arms into place, stuck the bolts through, did a quick tightening of the nut, stuck another bolt through, quick tightening of the nut. Was going through this process until I got to this one right here. You'll notice that this arm in this picture is hanging. I swiveled it up, attached it right there, tried to stick this long bolt through, and it got stuck. Now remember, we're all three standing in the bed of a truck. 100 pounds held over our heads. I'm furiously, frantically trying to get this bolt through. I'm jiggling it. Maybe I just didn't get it in there right. Slightly off, get it through. Thought about running into my garage real quick and getting a rubber mallet and just banging the thing through. And right as I was about to do that, I thought, it shouldn't be this difficult. I shouldn't have this much trouble. The whole thing has been smooth so far in terms of the installation. It shouldn't be this much trouble to try to get one bolt through one hole. So I went and grabbed the instructions. I had used the instructions flawlessly and religiously through the whole process. And I'll tell you, even to this day, if you take a level and go out there and stick it on this post, you're going to find that it's perfectly level on all four sides. I spent hours being meticulous about the installation of this thing. But obviously something was going wrong. So I'm furiously scanning through the diagrams and looking through the information, trying to figure out what went wrong. And I'm reading this. Attach the long leg of upper arm, number 6. You look over at the diagram. It's here, number 6. These are the long legs of the long leg of the upper arm, number 6, to the top pole, number 3. That thing right there, as shown in Figure 7. Now it refers it to a figure using a bolt, number 7. Or if you're a fan of this one, right here. 2 flat washers, number 18. 2 spacers, number 8. Not real sure what the spacers are here. Is it this thing, and this thing? I don't know. And 1 lock nut, number 4. Now conceptually, it's really not that difficult, right? You're sticking a bolt through a washer, through an arm, through a spacer, through the post, through another spacer, through another arm, through another washer, and finally to another nut. And why are we doing this? Well, because we need these things freestanding so that when we install the basketball backboard, that we have something to attach it to right here. Makes perfect sense. Not that complicated, right? So what went wrong? This is what went wrong. I got things flipped. Tell me if you've ever done that. Just had one small thing, but I had it flipped. I had it backwards. I had it backwards like this. You'll notice in this picture you can see the mistake. If you follow the diagram, the long arm is here, the long leg is here. It says it right there. This is the long part. It's supposed to be attached to the post. And then you'll have the little short leg here. I've got it backwards. You'll notice I have the little short leg attached to the post and the long leg of the arm here. And the problem was the following, that these holes, the one here and the one here, are identical in size, and the only difference between the two is the placement of them. This one here is placed a little closer to the edge so that when you're trying to install the backboard, the bolt goes through. When you have it flipped, it doesn't quite match up. And it was the only thing that finally tipped me off that there was a problem. It's simply the bolt wouldn't go through. And so essentially, as you can see here in this red image here, everything was flipped around. I had it looking like this rather than like that. So what went wrong? Who is supposed to blame? Well, the obvious one would be to blame me. Kevin Garrison, the idiot. And that's what Donald Norman says we do. Invariably, people feel guilty and try to hide the error or blame themselves for stupidity or clumsiness. Now, obviously, when I've got two people in the bed of a truck holding a 50-pound backboard over their head, it's really hard to hide the error. It's obviously an error, and so I took the blame for myself. Now remember, I have a doctoral degree in technical communication. I teach technical writing. The two people who were in the bed of the truck were my former students who had taken technical writing with me. I felt like a complete idiot. I can't read a set of instructions well enough to install a couple of arms onto a basketball pole. Dumb me. So the temptation is to blame me. I have a hard time doing that. Not because I'm not stupid at times, but because of the following reason. Everything should be designed for a least competent user. That's a term in tech writing. The least competent user, the person who's the stupidest of all. I have a hard time believing that that's the case with myself. Obviously, I have a doctoral degree in English. I have a hard time believing that I'm the least competent user. I may be an incompetent user, but I'm not the least competent, the dumbest person of all. I also don't believe that the reason that this is the problem because of the following. Donald Norman argues that there are two types of errors. There's slips and there's mistakes. A slip happens when you drop into an unconscious activity. You're doing something automatically and you forget. So for instance, you unlock your car door, you get in there, you drive to your location, you take the keys out, you put the keys next to you, and then you get out and you lock the door. And then you have your keys left in there. You've done something automatically. You're not thinking about it consciously. You're thinking about what you're going to be doing when you get to the office for the day. And so a slip happens when something small takes place. It's just a minor slip up. I had this happen the other day. I was making cookies. Maybe I am, in fact, more than the least competent user. Maybe I am stupid. But I had the cookies in the oven. I took the cookies out, and I left the oven on. And my wife goes in and she's like, Kevin, the oven is still on. That's a slip. I mean, just an automatic behavior mode. I want to eat cookies. That's the end of making cookies. So I'm eating my cookies, and I forget to think about the other end, which is let's not burn down the house. So what actually happened here was a mistake. A mistake is much larger, and it happens when there is conscious deliberation. I was consciously deliberating what was supposed to happen when I was putting this all together. This was not an automatic behavior. I'd never done this before. So this is much larger. And because of that, I was tapped into this part of my brain, the conscious part. The old brain back here is 10 times faster, and it's very efficient, but it all does so, it works automatically. This brain up here is 10 times slower. It's very inefficient, but is able to work through a complex series of tasks very slowly and make it work effectively. So obviously, in the process of being extremely conscious about what was going on, I still made a mistake. I still had an error despite having all this abundance of resources right here. So I refuse to believe that it's the stupid user answer. So hypothesis 2, maybe it's the stupid designer. Maybe I need to blame them. That's the obvious temptation, right? It's not me, it's you. So for myself, there's a couple of places I think I could blame. The first is the conceptual model and the way that the conceptual model works. The conceptual model is not really the problem. The way that it works is simply this, is that the designer has a model for how things work and the user has a model for how things work, and then that all comes together in the actual system itself when you're putting the basketball goal together. Now, if everything's matched up, everything's good. Obviously, things didn't get matched up, so what went wrong? Well, what didn't get wrong is the conceptual model. I understood what was going on. We needed to put two arms to the post so that we could mount the backboard to the two arms. I understood that on a conceptual level. That's not a very complicated thing to understand. More importantly, if you think about it in terms of the way that everything works with the conceptual model, it wasn't their fault. It's not the designer's fault. There's plenty of natural mappings and affordances within this design. Here's an example. If there's a hole, something goes in the hole. That is as natural as it gets when it comes to mapping. This is Sex 101. This is something we teach our children. There is a cave, and there's something that goes in the cave, right? And so if we're talking about in terms of what's natural, we understand that if there's a hole here and there's a hole here, something had to go through the hole. And in terms of affordances, it was perfectly thought out. This particular bolt only goes in a specific size hole. If the hole's too small, it won't go in. If the hole's too big, then it rattles around. So we find the perfect size hole with the perfect size bolt, we stick it in there and it works. So it's not really a problem with the conceptual model. And it's also not a problem, as Donald Norman talks about, in terms of creeping featureism, where they're just simply stacking features on top of features. All of these things are necessary. For us to have the final goal of a basketball goal, we have to have all these component parts. You have to have a backboard, you have to have a rim, you have to have a pole, you have to have the arm to attach the pole to the backboard. None of these are things that you can take out. So it's not a creeping featureism problem. It's not like my phone over here that I can't figure out because there's 80,000 buttons and things that I don't need. All I want to do is pick up the phone and call somebody. It's not a creeping featureism problem. So I really fail to blame the designer. It's not my fault. It's not the designer's fault. They understood what they were trying to accomplish, and I understood what they were trying to get me to accomplish. So maybe it's the instruction's fault? I don't think so. Everything is extraordinarily visible. Visible both on the goal itself and visible in the instruction. There's no problem with selective attention either. I mean, there's a lot of information. It's a 15-page document. There's a lot of diagrams, but there's a redundant amount of information. There's copious amounts of information. And you can figure out what's going on based on all of the different images within. It's also standardized. It's not like they were using anything besides what a standard ratchet set and a standard Phillips head screwdriver would use. So everything's already been standardized. So I refuse to believe it's my fault. It's not their fault. And it's not the fault of the mediator between those two groups. It's not the fault of the instructions. So who is at fault? You're going to love this. Donald Norman says in page 129, the real culprit almost always is the design. And here's where the problem slips in. It's really straightforward. Conscious thoughts are severely limited by the small capacity of short-term memory, 5 or 6 items. The most recent study I've seen on this says that the number is actually closer to 3 to 5. For years, everybody assumed that it was 7 plus or minus 2 for working memory. It's actually closer to 3 to 5. 4 plus or minus 1. You have very small capacity for working memory. And if you can go above 5, it's because you figured out a way conceptually to join things together, to be more efficient. And notice how many things that I have to think of in order to get this step to work. I've got to attach an action. I've got to get an object, the upper arms, which are demarked by this really goofy thing, number 6. And I have to have specifically the long leg of the upper arm, which is marked by that stupid number 6. So I'm already conceptually within 4 or 5 words, kind of in a very abstract world. Attach this, what am I attaching? The long leg of the upper arm. And that doesn't even make sense if you're thinking about it, because this is an arm and this is a leg. So I'm now having to reconceptualize it in terms of a metaphor based on the numbers attached to this number 6. What am I attaching it to? The top pole, which is number 3. These are all arbitrary numbers, as shown in figure 7. Oh, now I get to see figure 7. You would think it would start with, say, take a look at figure 7. All the things you need to know are here. Using a bolt, flat washers, 2 spacers, and 1 lock nut. Again, I mean, this is way more than 3 to 5 things in the conscious working memory. And the only way that I got it to work was to have the instructions here, to have the basketball goal here, and to be trying to work simultaneously between the two. Get this? Okay, I've got that. Now I need to get the next thing in the conscious working memory. Now the next thing. And I swear I completely just skipped over that little line right here, where it says attach the long leg of upper arm number 6. I did not see that long leg. I don't know how I didn't see it. It's right there. Bolded, all caps font. Long leg. I didn't see it. So, how would we fix the problem? I have 2 recommendations based on the principles of design from Donald Norman. One, he says on page 55, put information in the world. Why couldn't they? I swear I don't understand why they didn't do this. Why couldn't they put little peel-away stickers on all the different components telling us this is the top of the pole, this is the bottom of the pole. This here is the part of the arm that attaches to the backboard. This is the part of the arm that attaches to the pole. You're talking minimal cost, but put that information out of the document and put it into the world itself, into the artifact, so that I can see it, I can read it, and I go, oh, okay, this is where it attaches here. Or, page 55, don't require great precision or use natural constraint. When you have the same size holes here and here, that's a chance for a lot of problems. You need great precision to make that work. Or the natural constraint, why not make one hole slightly larger or slightly smaller than the other? I would think that connecting this thing here would require a bigger bolt than this here. So why not make this hole larger, this bolt larger, and this one smaller, and the bolt smaller, so that it's easier for someone to quickly figure out, I've got the wrong hole. Simple solutions to a complex problem to make sure that my two friends who are holding 100 pounds over their head don't drop it on their head, don't drop it on my head, and that I don't look like an idiot despite having a doctoral degree in technical communication. Alright, so let's recap real fast here. We can blame the user, we can blame the designer, and we can blame the mediator between the two. But Donald Norman's fundamental argument is that the best approach is to always blame the designer. I'm going to leave you with what I think is the most powerful passage in his book, which is where he's trying to explain why the 3 Mile Island nuclear power plant had a problem. He says the following: operators pushed a button to close a valve. One action caused another, right? The valve had been opened properly to allow excess water to escape from the nuclear core. In fact, the valve was deficient, so it didn't close. The button was pushed, and rather than closing, it stayed the same. But a light on the control panel indicated that the valve position was closed, and the light actually didn't monitor the valve, only the electrical signal to the valve, a fact known by the operators. Still, why suspect a problem? The operator did look at the temperature in the pipe leading from the valve, and it was high, indicating that fluid was still flowing through the closed valve. In other words, it wasn't closed. It was still open. There's things running through it. But the operators knew that the valve had been leaky, so the leak would explain the high temperature. But the leak was known to be small, and the operators assumed that it wouldn't affect the main operation, and they were wrong. And the water that was able to escape from the core added significantly to the problems of that nuclear disaster. The fault was in the design of the light and in the equipment that gave false evidence of a closed valve. Now, obviously, when you're talking about building a basketball goal, you're not talking about necessarily a life or death situation. When we're talking about an office space like this, we're not talking about a life or death situation when a student stops by and sits in a chair in interfaces with me about a class. We're not talking about life or death. But if we reconceptualize our cognitive framework away from thinking about users as being stupid and rather thinking about users as being intelligent, and the reason they're failing our classes, the reason they're having a hard time interfacing with me, the reason they're having a hard time putting basketball goals together is not because they're idiots. Take that out. They're not idiots. And assume rather that there's something wrong with the design. We might have a fighting chance to recreate this technologically heavy world into something that's centered around users. Alright, I'm done. Have a good day. Goodbye.